Our next section of the lecture is going to be on linearizable models. So these are models that you can make linear through a transformation. We already talked a little bit about these, but I'm going to go through and talk about each of them. Fundamentally, what you're going to do is you're going to have to transform, fit, and then transform back is the idea. Okay? So the first one of these, probably the most important, is the exponential model. Y equals a e to the rx, something like this. And so remember, we talked about this in that you can transform this using a logarithm. So I'm not going to write natural logarithm ln, I'm going to write log. I always mean natural logarithms, though in practice it doesn't actually matter, it just changes the coefficient sum. So I'm going to take the log of each side. So log of y is log of ae to the rx. And so we know from our log rules that this tells us log y is equal to log a plus rx. Okay? So if we can fit a linear model, so if we fit a linear model to x comma log xi comma log of yi, that linear model is going to give us the coefficients for our exponential model. Okay, and so let me explain what I mean by that. So if we find that log y is equal to mx plus b, we can turn that back into an exponential function by exponentiating both sides. So if you exponentiate both sides, we get y equals e to the mx plus b, or if you prefer, y equals e to the b, e to the mx. So this e to the b effectively is our a, m is effectively actually our r. Okay? And so if you find a line mx plus b that fits the data set xi log yi, the corresponding exponential function y equals e to the b, e to the mx will fit your original data. Okay? And so we'll see how to do that in Excel. Effectively, it's actually the same thing as what we just did with the other terms, except now we're fitting, rather than using the original y and a bunch of different x values, we're using the original x and the log of y to do our fit. Okay? So we fit to that, and then we translate back. And we'll go through that in Excel. Okay? The next one I want to talk about, kind of the next natural model, is what's called the power model. So this is where you have something like y equals ax to the r, something like this, where you've got x raised to a power, but you're not sure what that power is. Same idea here. We're going to take the log of each side. This is called the power model. Log of y equals log of ax to the r. So log of y equals log of a plus r times log of x. And so you can see that this is a line where we've got an m, a coefficient, times log of x plus some coefficient b equals log of y. So to fit this, we fit a line to log x log y. Okay? And so if you've got a line y equals log of y equals m times log of x plus b, right? You can exponentiate both sides. Probably easier to combine. No, exponentiate both sides. So y equals e to the m log x plus b, y equals e to the b times x to the m. Okay? And so that's going to be your actual model, y equals e to the b times x to the m, that fits your original data set. And if you use that to get your predicted values, it should fit your original data. Okay? Another one that's actually pretty simple to see is a logarithmic model. So if you've got data that seems to be increasing but then slowing down, that could be a logarithmic model, right? That's what a logarithmic function looks like. Kind of flattens out. So logarithmic functions are of the form y equals a log x plus b, or maybe let's say, even to make it a little simpler, m log x plus b. And you can see that this is actually an example of an inherently linear function. It's similar to our this one actually matches what we did before, and so if we fit log x comma y with a line, we'll get this m and this b. Okay? So that's 3 examples of ones that we can do using logarithms to kind of manipulate exponential, power, logarithmic. Let's look at a non-logarithmic example, because I know you asked about that in class, and it is interesting to see some of those. And one good one is a hyperbolic model. Okay? So in a hyperbolic model, this is something where you have a vertical and a horizontal asymptote. Okay? And so if your data fits this vertical and horizontal asymptote, it looks like it's got that. The model you're going to try and fit it to is y equals x over ax minus b. Okay? This will have a vertical and a horizontal asymptote. You can see the horizontal asymptote is going to be 1 over a. The vertical asymptote is going to be x equals b over a. So you could just fit it kind of like that. You could kind of shoehorn that in and figure out what a and b are. But you can actually linearize this. And you can do that by taking kind of a sophisticated transformation where you let u equal 1 over x and v equal 1 over y. Okay? And so if you do that, if v equals 1 over y, y is equal to 1 over v. Okay? So you get 1 over v equals 1 over u, right? X is going to be 1 over x is u is x is 1 over u. So 1 over u divided by a times 1 over u minus b. And if you simplify this side, turn this into one fraction, what you get is 1 over v on the left. This u moves down to the denominator. You get 1 over a minus b u. Okay? And so if you flip both these fractions, right, which you can do it by flipping both sides, you get v equals a minus b u. And so this is linear in u and v, right? This is a linear equation. And so if you fit a line to 1 over x, 1 over y, the corresponding coefficients a and b are going to give you a and b in this hyperbolic model immediately. Okay? And so you can fit that. So this is an example of a linearization where we're not doing a logarithm, where we're doing something a little bit more complicated. Okay? So I'm going to go through, I'm going to do an Excel spreadsheet. I'm going to show you how to do one of these, just to show you the transformation back on the exponential, and then it'll have examples of the other 3 and how you can do them.